Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we proceed with lecture 8, that is 3D rigid body. And today motivational quote is positive thinking is a valuable tool that can help you overcome obstacles, deal with pain and reach new goals, by Emin Morin. And what have you learned before? You have learned for last week. You have learned about rigid body and the reaction at 2D support and equilibrium of rigid body. So today we will proceed with equilibrium condition for 3D rigid body and the free body diagram for 3D rigid body and analysis approach, example and exercise. So for the condition of rigid body, for particle, we only consider force. But for rigid body, we consider force here and moment. So for the moment, it is a rigid body condition. Okay, the procedure for drawing rigid body. First, you need to draw the boundary of the chosen section and separate it from all another bodies. For body with a mass, put the weight equal to mg acting at the center of gravity on the body, acting at the center of gravity of the body in the vertically downward direction. Okay, for example, you have something here and the mass is toward down with the m is mass and g is 9.81. Okay, and then put all the external forces. So if you have if there is a force here toward there, and if there is a cable, you need to that's it. For system involved with cables, force of the cable must act outward of the body. For example, here, if it is a cable there, and the force is outward from the body and must be in tension for the cable. And put the reaction. Okay, this is the important of rigid body, because for particles there is no reaction, but for rigid body there is a reaction where the bodies touches or connected to different rigid body. For example, you have a cantilever beam and there is a force there. So at the connection to the wall, there is a reaction here. And the body should also include dimension for the process of taking moment. Okay, dimension is important in statics. So you need to know there is the, for example, mass in kilogram or in pound, and then for distance, the length, either in meter or inci. Okay, for the rigid body, there is a reaction. So last week we already learned about the reactions in 2D. So today we proceed with reaction as support for 3D. Okay, as general rules, if support prevent translation of a body in given direction, then a reaction force acting in the opposite direction is developed. So the reaction force is in the opposite direction. Similarly, if rotation is prevent a couple moment exerted on the body by the support. Okay, previously we have, for example, we have cantilever beam, and to know the reaction force, so we need to consider, do this cantilever move in the x direction? Okay, cannot move, so there is reaction at the x axis. So there is AX here represent the reaction at the axis. And can this cantilever beam move in the y directions? For example, can this beam move up and down? Cannot, because it is fixed at the wall, so cannot move. So there is reaction at the y direction. So there is reaction here, AY. Okay, now for the same cantilever beam, for this one I forgot. For this one, there is a force here, and when we apply force, there is a moment toward, this means moment in the clockwise direction. So here the reaction is in the opposite direction. So here there is moment reaction here. This means opposite of the moments. Okay. The reaction force of the moment in the counterclockwise. Okay, and here for this one is for 2D, and for 3D there is for 3D we need to consider x direction, y direction, and z direction. This one include force and moment. Okay, for this one, okay, this is cantilever beam, same as before. So can this beam move toward x-axis? Okay, cannot move. So there is a reaction in the x-axis. So for example, here there is a moment here, and then y direction also cannot move, so there is y here. And there is another axis. This one is AX, AY, and another here AZ. Because it also cannot move horizontal like this. So there is AZ here. And is this cantilever beam can rotate toward x, y, and z? Cannot. So this one there is there is a rotation moment here, and X here, and Y, and here, and Z. Okay, I will explain this in the next slide. So what I want to explain here, that's the concept is if it cannot move, so there is a reaction in that direction. Okay, this is the list of reaction for 3D support. Okay, for example, here there is a cable. This is the list of reaction for 3D support. Okay, firstly we have a cable, so this is a beam, and there is a cable there. So okay, for example, we have here we have this cable can move freely, X, Y, and Z, but it cannot move. No, pardon. This okay, this cable can move in this direction and ups and down, but it cannot move toward here. Okay, cannot move here. That's why there is a reaction here. So F is this one is use the F, but previously we used A, so it's like A here. So this reaction is toward the cables. And for the smooth surface and support, okay, this one, this structure on the smooth surface, so it can move, for example, it can move in horizontal and vertical. This one can move, so no reactions. But it cannot move downward. Cannot move downward. So that's why there is a reaction upward. Okay. And this, the third one is roller. So this roller, even this is okay. The rolls is for this current reaction is toward there, but it also can move in the horizontal direction. So it can move. Okay, this it can move X and Y. So no reaction. But this one also cannot move in the Z direction, so there is reaction in the Z direction. This one is Z direction. And the fourth one is ball and socket. Okay, this one is ball and socket, so it can rotate. So it can rotate, so no moment. no moment reaction. But this one, because it's fixed to this ball, it can translation, so it cannot move. So for example, this one is x, y, and z. Okay, cannot move in y direction, so there is reaction there. And also cannot move in x direction, so there is reaction in the x direction. And also this one cannot move up and down, cannot move in z direction, so there is a reaction force there. So but there is no reaction moments because it can rotate there. So the reaction is in the x direction, y direction, and z direction. Okay. The fifth is single journal bearing. Single journal bearing is there is okay. The fifth is single journal bearing. Okay. For this fifth and sixth is both if bearing. But for the sixth is square shaft. Square shaft means this long structure in the cross section is square, and this cross section is circle. So by this condition, you need to understand how it's moved. So for the single journal bearing, this one is a long circle shaft can rotate in the okay, this one is this x, y, and z. Okay, this long shaft can rotate in a x in the y direction. So y direction can move. So no reaction force. Okay, but in the x directions, this shaft cannot move in x direction here. X direction cannot move. So there is reaction. That's why here there is Ex here. And this long shaft also cannot move in the z direction. So for z direction cannot move, so there is reaction. This one is okay. And this okay, we already consider the force reactions, and then we need to consider the moment. Okay, in the x directions, this one can move freely. This means can move clockwise, counterclockwise, the long shaft. So in the x directions, can rotate. So there is no moment reaction. But in y directions, y here, this one okay, cannot move here, and also cannot rotate in the y direction. So cannot rotate. So there is a moment. That's why there is also sorry, this one. Okay, we have considered the force reaction. Now we need to consider the moments of these reactions. Okay, for the firstly x direction here. So is that it can move. Sorry. Okay. Is that this long shaft can rotate in the x direction. So it means moment at the x axis. So cannot rotate. So there is reaction of the x axis here. So that's why we have mx. And then for the y direction, y is here, and is this long shaft can move rotation of the y axis. So it can rotate because it's free. This one is this long shaft can move in the y direction and also can rotate with the y axis. So it can rotate, so no reaction in the y axis. And for the z directions, z is upward, so is this shaft can rotate with the z axis. Okay, cannot rotate, so there is moment reaction. So there is mz here. Okay, this one is for the single journal bearing with circular cross section. Okay, how about the single journal bearing with square shaft? This means this shaft have square cross section. So it's like this. Okay, and it's same like before. We have x, y, and z. And we look for the force reaction first. For the x-axis, is this square shaft can move horizontally in the x direction. Okay, x direction. Cannot move. So there is reaction in x direction. So there is ax here. And for this y directions, it can move or not in the y direction here? Can, right? Because it this one is not fixed. This one it can move along the y axis, so it can move. So no reaction. So there are no reaction in the y axis. And then for the z direction, is this square shaft can move up and down? Cannot, right? Because it's already fixed with this bearing, so cannot move. There is a reaction. the in the z-axis. So there is AZ here. Okay. And then we look for the rotation. For the x directions, is this long shaft can move in rotate with the x-axis? Cannot rotate. So there is a moment. So there is a moment here. Moment reaction mx. And this one, okay, this is what's different between the single journal bearing and single journal bearing with square shaft, because okay, here for the circle cross section, it can move in the y, it can rotate with the y axis, but because the cross section is square, it cannot move. So here this is y-axis, and do this long shaft can rotate with the y-axis? Cannot. So for the y direction, cannot rotate. So there is a reaction moment here, and y. And is this single journal bearing with square shaft can rotate with the z-axis? Cannot rotate. So there is a reaction. Sorry, there is a moment. So there is moment here. And set. Okay, we proceed with the another 4. Okay, previously there is a single journal bearing, and now we proceed with single truss bearing. Okay, this one single truss bearing. So single truss bearing is fixed. This means it's similar to fixed because it cannot move. Okay, we proceed with another 4 reaction and the condition. So the next is single truss bearing. So for single truss bearing, it's similar with previously, that is single journal bearing, but this single truss bearings, this one, it has bearing here, but this shaft only can rotate, it cannot move. So okay, so for this one is this is x, y, and z. Okay, so in the x directions cannot move, so there is ax, the reaction at the x. And also for the y, because okay, this at the y direction, it cannot move, so there is reaction at the y direction. So there is a y here, and also a z, because it cannot move up and down. And when we look for the rotations for x, it cannot move with the axis of x, so there is a mx here, mx, but it can, okay, this one is for y direction, so for the y direction it cannot move, so there is a reaction, and it can rotate, so no moment reaction. So there is no moment reaction at the y, but at the z axis it also cannot rotate. So that's why it has here moment z. Okay, and for the eighth connection is single smooth pin. Okay, single smooth pin is like we have pin here, and it can move like this. So same here, we have x, y, and z. So this structure cannot move in the x. So that's why we have ax here. But with this rotation, what I draw here, this one and this one, the center or the axis of this rotation is x-axis. So there is moment, there is rotation at x-axis. So no moment reaction. But for the y, it also cannot move with the y-axis, and also cannot rotate with the y-axis. That's why we have ay here and also my here. Similar with z, it also cannot move up and down, so there is a z here, and also cannot move with the z axis, there is mz here. And then we proceed with single hinge. Single hinge is like our door, so we can open and close. So here we can have x, y, and z. So when this one, what this hinge can do is it can rotate like this. It can open and close like that. So this one cannot move in the x direction, so we have the reaction at the x, and also cannot move up and down is z, and also cannot move horizontally, so there is a y here. But for the this movement, for example, if we want to open and close, so this one, the center of axis is y-axis. So at the y-axis there is a rotation. So that's why no reaction moment. So but for the x and z, they can there are no rotation, so there is a reaction moment reaction here. So mx and mz here. Okay, the last one is the fixed spot. So fixed spot is we have like pillar. So for example, we have pillar that's fixed on the ground. So this pillar cannot move. That is fixed there. So it cannot move outward, downward, right, front and back, right and left. So the reaction is all. So there is a ax, ay, az, and also it cannot move. So there is a x and y and mz here. Okay, so until now, do you understand the how to determine the reaction of the structure? So this one is the simplification. For example, reaction with one unknown. So we have, for example, with ball. For ball, the unknown is 1. So ball, or previously it's called as ball and socket. Ball and socket also same like this. Sorry, ball and socket is different. Okay, this one only ball. So this is same with roller. Ball or roller. So it has only one toward up. Also frictionless surface or smooth surface. So the unknown is one unknown. One unknown toward up. Okay, and for the reaction at support with two unknown is roller and rough surface. So roller and rough surface. Okay, this one is maybe I'm not explained before. This is another type that we this roller can move only at one direction. So it can move only at the, for example, here is Z. So Z direction. So that's why the reaction is A Y A Z A X. Okay, to make you more understand, this one is roller on rough surface, so it's only can move in one direction. So that's why it's a reaction at AY and AX. So this one, for this kind of reaction, it's more preferably ball, because roller usually at one direction. So this one you consider this one is ball, so it can move in this direction and this direction. So that's why the reaction force only toward up. And then okay, same with the wheels on rails, because it has rail here, so it's only can move in z direction. That's why the direction is at ay and ax. So there is two unknown. And for the three unknown, for the rough surface, because for this rough surface, the surface is rough here, so it's considered cannot move in this direction, uh, and for sure toward up, toward down, there is uh, no translation, so there is reaction toward up, toward x and z. Same with ball and socket. And for the support with for unknown, for example, okay, here also another connection. So another connection here is a universal joint. For this one, it's already joined together here, so it cannot move in the x direction. So there are reaction as the x direction, and it also cannot move in the z direction. That's why there is a reaction at the z direction, and also cannot move in the y direction, so there is a reaction at y direction. But this one, this joint can move like this based on this structure, so it can move clockwise and counterclockwise with the x-axis. Okay, for the reaction as support with four unknown, there are example of universal joint like this. So this is also new. I not explained yet this type of universal joint before. So this one, you need to imagine how this structure function. This one, how this structure move. So this one, okay, we start first with, okay, here we follow this x here. So can this structure move toward x direction? So it cannot move, so there is reaction here of ax here, and it also cannot move toward up in the y directions, so that's why it have reaction with the ay, and also cannot move with the z axis, so that's why we have reaction of az. Okay, and here, okay, how only this moment mx, there is only one reaction moment. Okay, first you need to imagine how this structure move. So this one, we have 1 and 2, and it's fixed with this joint. So okay, this one, you okay, consider this one is 1 and another one is 2. So for the first structure, it's okay, it can move like this. Okay, And another structure, okay, how you want to, okay, this one, the U form this, okay, you consider this and it can move rotation like this, and for this one it can move rotations like this. Okay, so this rotations, the axis is like this, and this rotation, the axis, okay, this one, okay, this one is rotate with the axis here. Okay, so we have considered the reaction force, and now we look for the rotation moment. There is moment reactions. So here you have this 2U structure. Okay, for example, this one is 1 and this one is 2. Okay, now you need to imagine how this structure move. So for the first one, okay, for the first one, it's fixed here. And how the first structure can move? Okay, you think it first. Okay, so for the first, it can rotate like this. Yeah, that means you hold here and you can move right and left. So it's rotate like this. So the axis is y axis. Because it can rotate in the y axis, so there are no moment y. No reaction moment at the y axis. Okay. Now looks at the second structure. So how this structure can move? So here you hold the holder here, and because it's fixed here, it can move up and down like this. This means it can move up and down. So the axis of this rotation is Z axis. So no moment at the Z. Okay, how about X? So this X is this. Okay, this one is X axis. Can it move like this? Okay, cannot, because it, okay, maybe you can say it can move, but the, okay, for rotation as the Y and Z axis, it is more than 90 degree, but movement but rotation at X axis only small. Maybe you can say it can move, but only with small degree of rotations. It's be less than 60 degrees, so it's not considered rotate. So this one have moment reaction. So there is mx here. Okay. For the reaction at support with 6 unknown, for example, is fixed support. Because for the fixed, it cannot move at all directions and also cannot rotate at all axes. So that's why we have 1, 2, 3, 4, 5, 6 reactions. Structure with 4 unknown is bearing supporting radial loads only, or previously we called this as this one is single journal bearing. This one is same with single journal bearing. Okay, so this one because this one it can move with the, this one is x, y, and z. It can move with the x directions, and it also can rotate with the x direction. So that's why no reactions at the x axis, but it cannot translate with the z directions, and also cannot go up and down. So that's why we have AZ here and AY here. And this structure also cannot rotate with Z and Y axis. So that's why we have another direction that is moment Z and moment Y. For reaction with 5 unknown, the example is pin and bracket, or we call previously it's called single smooth pin, or this one is hinge. Okay, this one is hinge, and bearing supporting axial thrust and radial load. So this one previously we call this as single thrust bearing. So this is hinge and single thrust bearing. So this one it cannot rotate. Sorry, it can rotate here. It can rotate with the x-axis. It can rotate like this. So also can rotate like this, but cannot move. Cannot move in the x direction. So that's why we have 5 unknown. All for the force. Okay, but for the x-axis, no reaction moments because it can rotate with the x-axis. But for the z and y, there is moment reaction. Okay, that's all for the list of the reaction as the supports. What you need to remember for every solution, every problem with rigid body, so you need to draw the free body diagram and need to know every force component and reactions, and also know this for the moments it's use cross and dot product. Yeah, for rigid body is quite complicated, but with a lot of exercise, inshallah you can understand the concept. Okay, and for the if there is more equations, because there are more unknown, so you need to do the solve the equation first. Now let's try to do this example. So the system shown in the diagram is in equilibrium. Determine the tension. Okay, so what's this question one is the tensions in the cable AC and tension in the cable AD and the reaction at the ball. So reaction at the ball. So there are three things that this question one. Let's try these examples. So this system show about okay diagram is in equilibrium. Determines the tensions in the cable AC and AD. So what's this question one is the first is tension in AC and the second tension at AD and the reaction at the ball and socket. So the third one is reaction at the ball and socket. So when you have a system or condition, first you need to do? Yes, first you need to draw the free body diagram. So this free body diagram based on previous, so we have beam here and then there is force to it down with 840 newtons and there is cable. Okay, cable here like what we have lens. Okay, this one we have cable 1 and 2 and this cable when we represent in free body diagram, the direction is outward from the body. So this is TAC and this one is TAD. Tension. So what's this question one? This question one the value of TAC, value of TAD, and another one is reaction here. Reaction at the ball and socket. Okay, so when you already this one. Okay, this one you have TAD. TAC, TAD, and the reaction at the ball and socket. So here, here the reaction is ball and socket. So let's look for ball and socket. Okay, this is ball and socket condition. So you have 3 reaction force at the all axis. So that's why for this one, okay, this one is ball and socket, and the reactions is represented as O. So there is OX, OY, and OZ here. The reaction force, and then okay, first we need to solve for the component of the forces. So this one the force toward down and it is at the toward down and this is downward y, so negative G. 840 and J negative. And then solve for tension in cable AC. So this is 3D force by using dx over d and dy over d also. So we have for TSC the the equation is like this. Okay, this one. Okay, we have because we don't know the value of TSC, so just put TSC here. So we have TSC in the I direction, J direction, and K direction. So this is equation for TAC. And then for the tension in TAD, same like TAC, so you have the equation is like this. And also for the reaction, we have the X, Y, and Z, so it's represented. Just put OX, OY, and OZ here. Okay. And for equilibrium, we have that force X equals 0, summation of Fy equal to 0, summation of Fz equal to 0, and summation of Mx equals 0, summation of My equals 0, summation of Mz equals 0. This is the condition for equilibrium for rigid body in 3D. Okay, so this one for X component, the equation is like this. This is X or I component, and or I, Y or J, it's like this. That means you plus everything in X directions and plus everything in Y direction, and also plus everything in Z direction. So it's equivalent to 0. So you have 1, 2, 3 equations. And another one is, okay, until now, until this one, it's all about force only. Okay, this one we already consider 1, 2, 3 equation for the force. Okay, then we need to consider for the moments. Okay, how this moment exists. Okay, we look again at the system. Okay, here we have 1, the force is 1, 2, and 3. There is 3 force that result in moment at O. Because for example here, when the force toward down, this will it will move like this. This beam will how to imagine this beam will move with the rotation of Z axis. This one is moment. Okay, and this one also, if we pull this cable, it will create moment also, and also if we pull this beam using that cable, also create moments. That's why here. Okay, here we have 3 moments. Okay, this one is moment due to the F, and this one is moment due to tension AC, and this one is moment due to tension AD. Okay, so solve one by one. So this one for the force negative 840 Newton J, and the distance is ROB, and ROB is 1 meter in the x direction. Okay, let's see. Okay, how get 1? Because this one is x directions, and 0.6 plus 0.4 is equal 1. Okay, so the distance is 1 m in the x direction. And for the for the moments, do the cross products. So the moments in this one is the moment of the due to the force. Okay, and then we proceed with the moment due to the tension AC. So the ROA is 0.6 meter I, and okay, this is TAC. So it's cross products. So it's become this one. This is the moment due to the TAC, and then moment due to the TAD we get here. This is the equation for moment of TAD. Okay, when for the equilibrium, so all of this is for 1, 2, 3. Okay, and summation is equal to 0, and when you solve it, you will get the tension of the cable TAD and TAC here, and then put this value to get the OX, OY, and OZ. Okay, you can try to put the value of TAD and TAD and get the OX and OY and OZ, so we can discuss in the next sessions. And the last one, okay, try to do this exercise. Okay, that's all until now. Any question you can we can discuss in WhatsApp group. So that's all for now. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.